Okie dokie. Let's resume. Let's see if I can even remember where we stopped at. I skipped the day yesterday because I was so busy. But thankfully, I just rarely ever turn off this computer. Um, Watch, it just ends up turning off after I say this. But restart extensions. Okay. For whatever reason, a theme needs to update, which is really weird. Okay. So, um, we have a conversation, right, with this person named GCC. And I think it's kind of worth um, reading over because it does give us insight to like some of this whole like, why do I have to compile before I see my changes? So, yeah, let's do that together. So the compiler exposed. This week's interview. What has GCC ever done for us? At first says, may I begin by thanking you, GCC, for finding time in your very busy schedule to speak to us. GCC, that's not a problem, my friend. A pleasure to help. GCC, you can speak many languages. Is that true? Well, I am fluent in over 6 million forms of communication. Really? Just teasing, but I do speak many languages. C, obviously, but also C++ and Objective-C. I can get by in Pascal, Fortran, PLI, and so forth. Oh, and I have a smattering of Go. Whoa, so that's saying that GCC isn't just a compiler for C, but also a compiler for C++, Objective-C, and again, like Pascal and Fortran. And I actually didn't know that GCC could also compile Go. So that's pretty cool. So it's like a general tool for compiling. And I think it's called like GNU Compiler Collection or something like that. So pretty cool. Head first. Okay. On the hardware side, you can produce you can produce machine code for many platforms, virtually any processor. Generally, when a hardware engineer creates a new type of processor, one of the many things she wants to do is get some form of me running on it. So GCC is actually cross platform. So it not only runs on like x86, like this computer that we're on right now, but also on ARM. So that's pretty cool. It means that you can actually write this C program here and have it run. Like if you compile it for another hardware platform, it can actually run on that platform, right? So like it's just in a way kind of like JavaScript and Python that it can run in various different platforms as long as those interpreters are available for the platform that you want to run on, right? So in this case, your C code can technically run on a different hardware platform. So as long as you compile it for that platform. So how have you achieved such incredible flexibility? So GCC says, my secret, I suppose, is that there are two sides to my personality. I have a front end, a part of me that understands some type of source code. Written in a language such as C? Exactly. My front end can convert that language into an intermediate code. All of my language front ends produce the same sort of code. Wow. So GCC has two parts to it, right? So like the first part, right, just takes in a file, like for instance, like a C file, and then probably produces like a in this case GCC says intermediate code, so that's like the code that is before machine code, right? Machine code is basically the code that your CPU understands, so in this case x86, ARM, and so on, right? But that intermediate code is like kind of like code that's not really that type of machine code just yet. So yeah. You say there are two sides to your personality? GCC says, I also have a backend, a system for converting that intermediate code into machine code that is understandable on many platforms. Add that to my knowledge of the particular executable file formats for just about every operating system you've ever heard of. And yet, you're often described as a mere translator. Do you think that's fair? Surely, that's not all you are. GCC says, well, of course, I do a little more than simple translation. For example, I can often spot errors in code. So yeah, so whenever we try to compile a C program, sometimes we make mistakes, right? And when we make mistakes, we actually get errors in output right here. It's like, for example, I think we made a mistake somewhere up here. Yeah, right here. Like not exactly an error, but like oopsie, not exactly like an error, but like a warning, right? So like GCC kind of is in charge of telling us whether or not we're actually doing the right thing in our programming language. Okay, so what are some examples? Which is what head verse is essentially asking. GCC goes, well, I can check obvious things such as misspelled variable names, but I also look for subtler things such as the redefinition of variables, or I can warn the programmer if he chooses to name variables after existing functions and so on. So you check code quality as well then? GCC goes, oh yes, and not just quality, but also performance. If I discover a section of code inside a loop that could work equally well outside of a loop, I can very quickly move it. Wow. So yeah. So when you compile your code, right, and using GCC, for example, it just doesn't take your code and kind of does like a direct translation to machine code. It actually, tries to optimize your code a little bit, rearranges things so that it actually performs better for that platform. So there's actually various levels of optimizations, and they're like flags that you can pass to GCC. It'll be like GCC, like just forgive me, it's not correct, but it's like GCC optimize, blah blah blah, right? So like these different various like levels of optimizations you can target into your code, and GCC will try its best to actually move it around so that it performs better when when your program is actually being executed on the target hardware. There are caveats to it. Like, for example, I think like, let's say, for example, you try to optimize even more, right? Like a very high level of optimization. Sometimes that could increase the program size because it tries to like, for example, like, uh, take a loop, right? It'll try to kind of, for like, let's say you have a loop that's like 5 iterations. It'll try to like flatten that out and just do the thing 5 times, for example. So it's a very oversimplified example, but the bottom line is that GCC just doesn't translate your code. When it compiles, it tries its best to try to optimize it. Okay, so yeah, Head First goes, you do rather a lot. GCC goes, I like to think I do, but in a quiet way. GCC, thank you. All right. We're gonna skip this one here, but I encourage you to just go through every single page anyway. I don't want to be the compiler. So there's a solution. Okay, so the book has been uh writing this little project here, and we've decided to kind of deviate away towards that. So here they're using like, if statements and checking for things, right? I think we could do something similar with our current project that we're working on, which is the Caesarean cipher, kind of. So just like to review here, right? What we're trying to do is we have, let me just demo it actually. We have our little program that asks us for a letter A to Z, right? If we do Y, for example, we get the shift, right? And notice how I get like a tilde, right? But if I do H, for example, I get M. So that's like my letter that I input gets shifted by some amount to get like the encoded, or in this case encrypted version of the letter, right? But there are times where I might not, for example, get what I really want, right? Or because of my input. I can input any character at the moment. So that isn't exactly right. And I think, we should actually tweak our program a little to kind of check for the exact character and account for it and probably give some sort of error message. So we can do that first, and then we'll solve the problem. And like if we were to kind of overflow, like for example, we want to shift 5 times, right? But we input something like Y and we end up like in this spot with tilde, right? Uh, we kind of want to account for that, right? So let's just solve one problem at a time. So the first problem is we should only allow input from lowercase a to lowercase z. So we do that with an if statement. Where's the if statement that we put? So here we have our program. We define a shift to be 5. So we're going to shift 5 places, right? Up and down. In this case, just up. And we first ask the user for some input. Then we actually get the input here. So we ask for the input, and that input is just a single character that gets stored in this location. And so by the time this line is done, we actually have our input. And I think that's a good opportunity to actually check, right? Before we do all of this logic here. So it's just a simple if statement, right? If, right, since this is a character, we can check against characters. And internally, characters are just numbers by the ASCII table, right? So if input, right, is maybe less than A, for example, or input is greater than Z, right? We can actually print out some error. Printf, please input a character between A and Z, lowercase. Okay, and it will actually just return. Let's just return 1, meaning that there was an error code. So if our input is not in A, like if it's less than A, or it's greater than Z, right? Like more than Z. Let me just bring up the chart. Might be easier to show, right? So if our input is anything less than A, meaning less than 97, right? Or our input in this case is greater than Z, meaning everything after 122, we want to kind of not accept the input, exit the program, but we'll display the error message. And it's as simple as that, right? Like it's as simple as just hold on, I got text. Okay. So this is simply checking if our input is less than A or input is greater than Z. We'll print out this error message, and then we'll return 1 to kind of exit the program, right? Because return is to get out of the function, return some result. In this case, we have our main function, so we just return 1. That's it. So we'll try it out. So in order to compile, we gcc-o, or ooh, I'm losing myself. It's a long day at work. GCC main.c-o, right? Meaning output to cipher, right? And we want to execute cipher now. And if I did something like $, it will say, please input a character between A and Z. Okay, sure. All right. So that works, right? I gave it A and I got F again. How about if I do Z? All right. I got, oh, I didn't, I was supposed to get something, right? I was supposed to get an error. So why, right? Well, not an error. I did actually. No. I did. This is our second case actually. So let's see here. 1, 2, 3, 4, 5. I actually got the delete character, which is why it's empty. But yes, based off of our logic, this is correct, right? Like I did input Z. It's not greater than Z, right? I did put Z, but not greater than Z. So it's actually still taking in that input. It's just that when I shift, what ends up happening now is that I am adding 5, right? Because I defined shift to be 5. I'm adding 5 to the character Z, which is at 122 to get 127, and I'm at delete, right? Kind of don't want that. So what do we do? Well, I don't want to do any complicated math things, right? So I just want to kind of say, well, if your input plus the shift, right, happens to be greater than Z, in this case, right, just maybe roll over, right? Roll over, or just not handle it. Just error out, maybe. Maybe we can say, let's simplify it and say maybe too much of a shift. Let's keep it simple for now, right? Let's just keep it simple. Let's say, oh, shift is too high to handle encoding of this character. Why not? It's just a simple program. The goal is to just exercise our conditionals, right? So let's just say now it's valid input. Let's say it's something like Y or X or something like this, right? But if I were to do like X plus shift, which is 5, I'm going to go out of bounds, right? So what is our last character that's valid here? It's actually Z. So we say if our input plus our shift happens to be greater than Z, right? For example, going back to here, let's say we have U, right? If our character here, input U plus the shift, which is 5, happens to be greater than Z, then we exit, right? So in this case, 117, 1, 2, 3, 4, 5, right? 117 plus 5 is 122. It's still valid. But if we're at V, right? 1, 2, 3, 4, 5, we'll say, hey, well, oh, wait. 1, 2, 3, 4, 5. Yeah, we're at this opening brace, right? We'll say, hey, you could technically encode this character, but our shift is too much, right? So let's just redefine your shift. And so let's just do that. So if, our input plus our shift happens to be greater than Z, right? We'll also say printf shift is too large to handle encoding of this character. As simple as that, right? And we can say shift is currently, and we'll have a integer, right, as our placeholder, and we'll say shift. So this D here, %D for formatting, is going to get replaced by this integer shift here, which is 5, right, up here. So we want that message, and then we want to return 1 again. We'll save, and then we will compile again, right, and we'll run the program again. So, okay, let's just review, right? We'll have these two conditions here, right? So we'll have first, if we try to give something that is less than lowercase a in our ASCII table here, we want to give an error. Please input a character between lowercase a and z. Or if we go the other way around, where we're more than z, then we'll have the same error message. But let's say we pass that. But then if we, we pass this condition check here, but now we have a letter that is potentially going to overflow with a shift added to it. That we can tell by saying if it's greater than lowercase z, we can just say shift is too large to handle encoding of this character. And it will say the shift is currently blocked, and we'll still exit. Okay? So let's test it. So then I'm running this program. I said Z, right? I say Shift is too large to handle encoding this character. Shift is currently 5. Okay, how about, I don't know, percent. All right, please input a character between A and Z. All right, let's try a boundary case. Let's try V, right? Okay, shift is too large. That's true, but let's try U, right? We'll get Z, right? Let's try O. We'll get T. Okay, so that looks right to me. Yeah, so that's basic if else, right? Well, I didn't have any else here, but we're gonna go to that soon. Yeah, okay. So this is a pretty good exercise to just kind of get acquainted with just printing something out, receiving basic input, and then also just handling edge cases in this case. So I'm going to commit this to GitHub, right? Git add Caesarian cipher, everything under this folder. Git commit, handling edge cases, and I'll just git push. Okay, taking it very simple. Okay, what's next? Okay. Why not we actually now just try, let's see. This is switch statements, okay? Okay, let's do this. Let's actually try writing this code and going over what this actually is for once, right? So let's do that together. So we'll make a new project, right? We'll say maker cards, okay? We'll go in. I don't know why I didn't command line. I could have just done it in VS Code, but we'll just basically create a new file called main.c. And I think, based off of the time I have right now, I can just copy this code here for now and then kind of run it and check. And then we'll probably have to continue tomorrow, just simply due to time. I was running late today, so yeah, let's just, it should be really quick, right? Like we're just doing if else's here and, if else if, and I can explain that. So, yeah, so let's get started. Well, first, this is just a snippet, right? Do we need any libraries? It looks like scanf is part of stdio. I think put s2, so we still need to include, right, stdio.h, right? And then we do it main, okay? And then the first line is, so we're gonna copy this. We're gonna go with the reps. We need the muscle memory to type this syntax. So then when you put enter the card name, right? And then we're gonna so it's asking the user for the card name, and we're going to store whatever the user puts. It's a string with the %2s, and it's going to store 2 characters of that string into card name, so the array of characters here. So notice how we store 2 characters, but this is length 3 because the last element is going to be automatically the null character, right? So we can comment that last character is automatically null character, right? Okay, after that, we define a val, right? This is a card counting thing, it looks like. So that'll be like the total. No, this val is actually the card face value, it looks like. So we're going to check the first character of this card. So if card name, right, 0 has starts with the character K, what do? We say it's 10, right? Else if, right, if card name is actually a card name at 0, so the first character card name is character Q, right? We'll say the value is 10 again. Else if, I'm guessing if it's J, the first letter of the card name, string, right? Again, it's a string. We're just checking the first character, which is why it's index 0, right? We'll say character J is also 10. Else if the card name, the first character is, if the first character is A, right, with ace, right, we'll say val is now 11. Ooh, that's a special one. Otherwise, we just use this a to I, right, function with card name. And I think this is not, well, this is probably not part of stdio, maybe. But what this does is it takes a string, the entire string, right? This 2-character string, but 3 with an old character, turns the string into an integer, right? So a to I is a converter. See how it says int a to I? And then we drill down to it, right? Well, we can't, right? Because I think it does belong to a different library called stdlib. How do I know that? That's just practice, like over time, right? So we did that, and we drill into it. We finally drill into it, and the signature says, convert a string to an integer. And it takes in basically a string in this case. So that basically, otherwise, if the card first letter of the card name is king, right, we'll set the value to 10. Else if, we'll check else if the first letter of the card is Q, we'll set the value to 10. Else if the first letter of the card name is J, we'll set the value to 10 again. Else if the first letter of the card name is A, we'll set the value 11. Otherwise, we'll just blindly convert the string that the user had input right here, sourced from here, to an integer, okay? And then we set that as val. So now here there's specific card counting logic to check between so like if the value ends up being between I guess 3 and 6, right? We do something. Otherwise, if the value is 10, we have to like subtract. Okay. And I think they're just writing placeholders here. We have to put the logic ourselves, most likely. Yeah, so we had to implement that. The put s is here is like kind of like a placeholder saying, hey, you gotta do something here. So check if the value is greater than 2, meaning if it's 3, and at least less than 7, which just means that 6, right? We want to put a message saying count has gone up. Not too excited. Else if val is 10, right? We'll say puts count has gone down. Okay, so there's something I noticed here, right? Like, notice how with these if statements where there's only one kind of line after the block, there are no opening and closing braces, right? For if statements, it is perfectly fine to not have the braces underneath to cover the handler for the logic. But that could lead to a lot of weird bugs, in my opinion, because then you're relying purely on indentation, right? Which, again, C is not sensitive to indentation like Python is, and it's not sensitive to white space, right? So it can make code much harder to read, which is why I still put opening and closing braces, even though I only have one line following my if. It's just easier to read. You sacrifice like another line just, but you make the code much more readable. So I return 0 as the last line. Okay, usually when I copy like this, right, I like to test my program. So if I were to go here and go to cards, this is my directory, I'll compile main.c, gcc main.c, and I'll say output is going to be cards. And here we go. It compiles really fast because C is just super fast. So it looks like it's only like a 16 kilobyte file. So we'll run cards, right? And we'll say enter a card name. We'll just say K. So apparently, if we have K as a card has gone down. Because, why? By inputting K, we have value of 10 set. And at the end of this if else if, I guess, logic, we check to see if value is basically between 3 and 6. If so, count will go up. Otherwise, if the value is exactly 10, equal to 10, then count has gone down. In this case, since we had input K, the first letter is K, we set 10 to be val, right? And that's the reason why we end up in this case here, because we set to 10, then we do these checks. This is false, but this is true, so count has gone down. We did something like Q, same thing. We did A, right? Nothing happens because A is actually 11, right? But our logic doesn't check for that. It only checks for things from 3 to 6 or whether or not the value is 10. So that's basically it. That's the program itself. Now, is this the best way to kind of write this if else if? Excuse me, I need to take a sip of water. Oops. Okay. It's not exactly the best way when you have so many checks like this, and it's kind of the same. You notice it's like card name at 0, card name at 0, card name at 0, card name at 0. There's actually a better way to do this, or at least a more readable way, and that's called a switch statement, right? And basically, it looks something like this. And we'll rewrite that next time. So that's it for today. Thank you.